So hello everyone. In this lecture we'll be discussing about your full wave rectifiers. But before we dwell into the depth of this topic, let's have some recapitulation on the rectifier circuits that we have already discussed in our previous lectures. So basically, why these rectifier circuits are required? You know that many electronic equipments, they work with DC power supply, and the line voltages in our households as well as in our industrial connections, they are available in the form of AC voltages. Normally the domestic rated voltage is line to line voltage is 220 volts at 50 hertz frequency, and basically a circuit which converts, there are several applications where we require a circuit which converts a AC voltage to DC voltage. And such a circuit which converts AC voltage into DC voltage is called a rectifier. And normally there are many nonlinear elements like your vacuum diodes or semiconductor diodes, which are used for the process of rectification of a AC supply into equivalent DC supply. So basically there are two types of rectifier circuits. You might all be aware of this. So these rectifier circuits are half wave rectifier and full wave rectifier. We have already discussed about half wave rectifier in our previous lectures. So here in this lecture we'll be discussing about full wave rectifiers. So let's start with the basic diagram, or you can say the connection diagram or the circuit of a full wave rectifier. It is a simple center tapped full wave rectifier which contains a center tapped transformer with two diodes. The output from this secondary winding of your center tapped transformer is fed into these two diodes, and the load is supplied through load RL. Basically here it is supplied through these two diodes. Here the configuration, again, it can be explained with the help of this figure, that a full wave rectifier, it contains a center tapped transformer and two diodes D1 and D2 in addition to a load resistance RL as depicted here in figure 1. Basically the purpose of a center tapped transformer is to convert a sinusoidal signal into two equal sinusoidal signals which are 180 degrees out of phase. What does it mean basically? The voltage ES1 and voltage ES2 both have 180 degrees phase difference, but they are equal in magnitude. So here this is the center tap terminal, and this is one end of the secondary winding terminal, and this is the second end of the secondary winding terminal. And basically these two voltages ES1 and ES2, they are equal in magnitude, and they have a phase difference of 180 degree, or they are in 180 degree phase opposition. So here, in order to understand the operation of this circuit, the two diodes D1 and D2, they are considered to be ideal diodes. What is the property of an ideal diode? You are already aware of this. We have already discussed the property or the characteristics of ideal diodes in our previous lectures. Particularly during forward bias conditions, ideal diode acts as a short circuit, and during reverse bias conditions, an ideal diode acts as a open circuit. So the two signals, voltage signals basically, which are from the secondary of the center tap transformer, these ES1 and ES2, they are obtained from the center tap transformers and they are applied to the diodes D1 and D2. During the first half cycle of the input wave, the point A here, this point A, it is positive, and point B in this figure here, it is negative with respect to the common terminal, that is this common terminal or the center tapped common terminal. So the diode D1, basically during the first half cycle, the diode D1 it conducts, and the diode D2 is in reverse bias conditions. And because diode D1 is in forward bias condition, there is a current IB1 which flows through the diode D1 and through the load resistance RL. Here, this basically current IB1, it flows through this diode D1 and through the load resistance RL. And since here this diode D2 is in reverse bias condition, no current comes in this direction, and all the current which is passing through this diode D1, it goes through the load resistance RL, and it follows this path, basically the path of current IB1. So again, during the other half cycle, the second diode D2 conducts because it is in forward bias condition, and the diode D1 is in reverse bias condition. And because of this, there is a current IB2 which flows through the diode D2 and the load resistance RL. So from this figure, again, it can be explained that during the positive half cycle, this diode D2, it is in forward bias condition, and this diode D1 is in reverse bias condition. And again, a current IB2 flows through this, you can say, this arrows, they show the direction of the current IB2, and it again flows through the load resistance. So basically here, this is the input waveform, or you can say the voltage ES1, which is between the terminal, center tap terminal, and the point A of the secondary winding of the center tap transformer. So this waveform, it starts at 0 instant, and it completes the positive half cycle at pi instant, and similarly the total one cycle is completed at 2 pi instant. Here, when this ES1 signal is applied, basically this IB1 current flows through the diode D1, and this current is for the positive half cycle. So during this positive half cycle, this current IB1 flows through diode D1, and the same current it also flows through through the load resistance RL. And for this negative half cycle here, this diode is in reverse bias condition, and so no current flows through this diode, and no current flows through basically the load resistance from pi to 2 pi. Again, during the negative half cycle, the other waveform, other output voltage, that is ES2, which is in 180 degree phase opposition. You can see this ES1 and ES2 are basically in 180 degree phase opposition. So during the positive half cycle of the voltage ES2, the diode D2 is in forward bias condition for this time instant, that is between the time instants of pi to 2 pi, and again a current IB2 flows through the load resistance, and the direction of currents for diode D1 and for the conduction of diode D1 and for the conduction of diode D2, that is both the currents IB1 and IB2 are in the same direction, as can be visualized from this waveform. Now, if you merge these two waveforms for the currents IB1 and IB2, these two waveforms, you will obtain the total current which is flowing through the load resistance, and this current is IB1 plus IB2. It will flow through the load resistance, and it will be a continuous current starting from 0 to pi instant, and similarly from pi to 2 pi instant, and so on. So the current is unidirectional through the load resistance, and it is continuous also. So again, let's come to the circuit analysis of your full wave rectifiers. Basically, Here you know that in this circuit there is a center tapped terminal of the transformer, which is used as the common terminal for two voltages ES1 and ES2, and these two voltages are in 180 degree phase opposition, or they are 180 degrees out of phase. So here we can write that ES1 is equal to minus of ES2. Minus sign is just to show that they are in 180 degree phase opposition, and the total value, instantaneous value of these two voltages, it can be represented by a general sinusoidal equation, that is Em sin omega t. So if we want to calculate the average value or the DC value of the voltage across the load resistance for the full wave rectifier, it is given by EDC, and integration of the first voltage, that is ES1, from 0 to t by 2 time instant, and added to the integration of the second voltage from t by 2 to t instant, and the total, you can say this total voltage divided by the total time of one cycle of the voltage waveform. So if we calculate this, we will be obtaining the value of EDC, or the average value of the voltage across the load resistance RL for a full wave rectifier. So here we replace the value of ES1 and ES2 with the instantaneous values of the sinusoidal equation, and then we integrate from these 0 to t by 2 instants and t by 2 to t instants. And after simplifying this equation, we will obtain the total EDC, or you can say the value of EDC as 2 Em upon pi, where Em is the maximum value of the voltage waveform. Again, if you want to calculate the RMS value of the voltage across the load resistance, first we calculate the squared value of the RMS voltage. It is given by the formula, that is integration of 0 to t by 2 ES1 whole square dt plus integration of t by 2 to t instant ES2 whole square dt, and the total divided by the total time period. So here again we replace by the basic sinusoidal equations and we simplify it. We'll be obtaining the squared RMS value of the voltage as Em square upon 2, and if we want to calculate the value of RMS, it is equal to Em upon under root 2. So you know that ripple factor is basically a very important parameter for deciding the quality of the output voltage waveform in a rectifier circuit, and that is why we need to it is required to calculate the value of ripple factor either in half wave rectifier circuits or in full wave rectifier circuits. So here the ripple factor, it is given as the ratio of the RMS value to the DC value, and if you substitute the RMS value and the DC values which are obtained in the slide, that is EDC and ERMS, and you put it here in this equation and calculate, you find that the total ripple factor for this full wave rectifier comes out to be 0.48. So here it can be observed that basically the value of ripple factor, which is undesired AC component, it is less than unity, and hence the output of the full wave rectifier is prominent in DC component. It means we have the prominence of DC component here, and the ripple factor is less than unity. So now coming on to the efficiency of rectifier, that is how we calculate the efficiency of rectifier. You know that efficiency of any device, any machine, it is calculated as the ratio of output to input multiplied by 100 if you want to calculate in terms of percentage. So here the input power and the output power is in DC form, and upon this input power multiplied by 100 will give you the total efficiency of this full wave rectifier. And this PDC, it can be calculated as the value of EDC square into RL, and similarly the input will be ERMS square into RL here. So these two values, if substituted in this formula, will give you the total efficiency as 81.2%. So for a full wave rectifier, 81.2% of the AC input power is converted to DC output power. Now coming on to the points, that is peak inverse voltage. Basically, the peak inverse voltage of a rectifier diode in a circuit is the maximum reverse voltage across the diode. Basically the maximum reverse voltage, or you can say the reverse bias voltage, which can be applied across the diode. So for the rectifier circuits, peak inverse voltage of the diode, basically it should be less than the breakdown voltage of the diode. That is the voltage limit. Basically, what is the meaning of this breakdown voltage of the diode? Breakdown voltage means the voltage above which the diode in reverse bias condition, or you can say the PN junction in reverse bias condition, will go or reach the avalanche breakdown. So always it is desired that the peak inverse voltage of the diode, it should be always less than the total breakdown voltage of the diode. So the peak inverse voltage of the diode used in the full wave rectifier should be greater than the twice of the maximum value of the applied AC voltage. So this is basically a thumb rule for deciding the rating of the diodes which will be used for making the full wave rectifier circuits. So whatever is the maximum applied value of the AC voltages, the peak inverse voltage of the diode should be greater than the twice of the maximum value of the applied AC voltage. So keeping in view this thumb rule, we should select the value of diodes, or you can say the rating of the diode which should be used for manufacture, or you can say making this full wave rectifier circuit. Now coming on to the disadvantages of full wave rectifiers, there are many disadvantages of full wave rectifiers. So here, as discussed above, the peak inverse voltage of the diode used in the circuit should be twice of the maximum applied voltage. So each diode, such diodes basically, whose breakdown voltage is greater than 2 EM is chosen for this purpose. And basically higher breakdown voltage diode manufacturing is more costly, and so this can be listed as a disadvantage here. So basically in this circuit, specially designed transformers which are called center tap transformers are used. So to rectify the AC mains voltage, a center tap transformer of 0 to 220 volts is to be used. But in case of half wave rectifier circuit, these transformers are not basically used for making a rectifier circuit, and hence we can directly apply the AC mains voltage to the diode. So we have a lesser component in half wave rectifier circuit as compared to this full wave rectifier circuit. So the reliability of this, because there is one more additional component, so the reliability of this full wave rectifier circuit is somehow it is compromised as compared to the half wave rectifier circuit. So again, since the center terminal of the center tapped transformer is used as a common terminal or the ground terminal, negative DC output voltage may not be obtained by simply reversing the output terminals, but will be obtained by reversing the diode connection. So this is again a disadvantage. If there would not have been a center tap transformer, simply we would have changed for changing the polarity of the output voltage. Simply the reversing the output terminals would have been sufficient, but here it is not the case. We will have to change, or you can say reverse, the connection of the diodes. So we have some solved examples on these full wave rectifier circuits. I am not going to discuss these examples in this lecture. You can go through these examples, and if you have any problem related to these, I have solved this example basically, and if you have any problem in understanding these examples, you can come forward to discuss with me individually. So now coming to the second type of full wave rectifier, which is a bridge rectifier, and it is this connection or this configuration of full wave rectifier has some advantages over the previous, you can say, full wave rectifier. So whatever are the disadvantages that was present in the full wave rectifier circuit, it is normally removed in the bridge rectifiers, and the basic circuit diagram of the bridge rectifier is shown in figure 3 here. Basically in figure 3a we have these 4 diodes in bridge configuration, and they are supplied through a transformer which is not a center tap transformer. So here this circuit has 4 diodes which are connected in the 4 arms of a bridge, and hence the name bridge rectifier is there. To understand the working of this circuit, basically let us consider that during the positive half cycle of the input ES, the point A, this point A is positive with respect to point B, which is represented here, this point B. During this condition, the diodes D1 and D3, that is this diode D1 and this diode D3, they conduct, and the diodes D2 and diode D4, they are in reverse bias condition. And because these 2 diodes, they are in forward bias condition, the current flows in the load resistance RL in the direction of the arrow, which is shown in this figure 3a. So here the direction of current, it is in this way, that is here the point is at higher potential, the current is coming like this, it is flowing, and again it is going through this here, and again to this terminal. So during the next half cycle, the point B is positive. Here this point B, it becomes positive, and then the diodes D2 and D4, they will be in forward bias condition and they will conduct, and the diode D1 and D3, they are in reverse bias condition. So this also leads to the flow of current. Here the flow of current is in this way. Here you can see that this diode D3, it flows here, D3 current, again it flows through diode D3, sorry, this is not D3, but here it will go through this diode. This point is in forward bias, and here the current will flow like this. It will go through D2, then RL, and again in this way through D4, and it will reach here. So the current through this load resistance in both the conditions, it will be in the same direction. So here in this figure, it is well illustrated. Here you can see that this current, it is going like this and coming here, and then going through diode D4 and again reaching at this point, and this total circuit is completed. So from this figure 3b you can see the direction of current and basically how and which diode conduct and how this current flows through the load resistance. And basically during both the conditions, the current which is flowing through the load resistance RL, it is in the same direction. So here the output waveform of the bridge rectifier is also the same as in the case of full wave rectifier. So both the outputs, they are same, the direction of current is uniform, or you can say they are unidirectional. So what are the advantages of bridge rectifiers? Basically they do not require specially designed center tap transformer. There is no common terminal between the input and the output, so negative supply may be obtained just by reversing the output terminals. The peak inverse voltage across any of the 4 diodes in the bridge rectifier circuit is equal to EM, and like your other configuration which was it was 2 EM as it was in the case of full wave rectifier. So for the same output voltage, the transformer secondary line to line voltage in the bridge rectifier should be 1/2 of that used for the full rectifier. So the bridge rectifier basically supplies large amount of DC power as compared to the full wave rectifier. So we have again a solved example related to the a bridge rectifier. You can go through this problem, and if you find any difficulty, I have actually solved it. So if you find any difficulty, you are free to discuss it with me at any other point of time. So this was all about your full wave rectifier. Thank you.